Okay, so there was this, first there was a request to try to clarify the problem we had on the problem set about the constraints and the equations for the Schwarzschild geometry. So let me just give you the clarification now. See, in principle, we had four independent equations when we set the symmetries of the Schwarzschild geometry. These equations were, let me use the symbol E for Einstein equations. So E mu nu is equal to R mu nu minus half G mu nu. Okay? And the four equations, so the four equations were, so the Einstein equations are E mu nu is equal to 0. Einstein equations in the vacuum are E mu nu equals 0. And the four independent equations were E T T, E R R, E R T, and E alpha beta. These were the angle coordinates. This looks like many equations, but we know on symmetric grounds this is G alpha beta times some E tilde. So E tilde is the, where G is the metric on the unit sphere. So we had four in principle independent equations. The equations were these four quantities being equal to 0. 1, 2, 3, 4, all being equal to 0. These were our independent equations. Okay? Now, we know on general grounds that it's inconsistent to solve, but you remember we had two variables, A and C, I think we call them. You know, on general grounds that it's inconsistent, to solve four equations for two variables unless the equations are not all independent. Okay? Now the problem was to show that the equations were dependent, to derive using a principle what the relationships between these four quantities was, and then to check that that principle, the relationship that you get is actually correct in your algebraic expressions. Okay? So, since all of these four quantities are going to be equal to 0, you're not going to get consistency unless there were two identities relating these four in principle independent quantities. By identities I mean things that are just true not using anyone's equations of motion, but just true for algebraic expressions like a plus b the whole thing squared is a squared plus b squared plus 2ab. Just something that's just true without any further assumptions on the variables, just always true. Okay? Now, what were the identities in our hand? The identities in our hand were the equations d alpha E alpha beta is equal to 0. Okay? So these four independent quantities were not really independent. We knew that beforehand. Okay? Now, the question was treating E alpha beta first as abstract quantities which you don't touch. You just leave it as ETT, ERR, ERT, and E tilde. Compute in the Schwarzschild geometry what identities these should obey. Why do I say in the Schwarzschild geometry? Well, you might have thought, well, the identity should just be something like del R, E, R. So now we've got a free index. As we discussed in class, the free index can take one of two values to get something non-trivial, R or T. So suppose we've got R here. We've got del R this plus del T E T R plus whatever. Del alpha E alpha R. And so, this is the expanded out version of this. Okay? The point being here, however, this looks like it doesn't depend on what background we're talking about, but these dels here do depend on the background we're talking about. So now you can take this equation and expand it out into an explicit expression involving only derivatives of e's and explicit functions, because you use the gammas appropriate to the Schwarzschild geometry. Those gammas will then be in terms of A and C. So you'll get an explicit equation for ERR, ERT, In this case, you won't get ETT, but okay. But you know, these del's are a bit deceptive because there may be an ETT because of the gamma. Okay, so you get one equation here. Similarly, when you keep t free, you get another equation. So that the first part of the problem asks you to find these abstract relations between these quantities treated as abstract quantities. These four unknowns treated as abstract things. This abstract relation must be true because it follows from Einstein's equation and guarantees that you do not have four independent equations. You only have two independent equations because your four equations are something equals 0, something else equals 0, something else equals 0, something else equals 0. If there are identical relations, two identical relations between these four independent quantities, you actually have two equations. Okay? So that was the first part of the question. Find in abstract what these relations are. Then the second part of the question is to check that we've done our algebra correctly. So we know exactly what these expressions are in terms of A and C. Since this thing has to be an identity, now if you put in what these expressions are in terms of A and C, you should just see that you get an identity without using any equations of motion, without using any properties of A and C. So these were the two parts of the problem. Is that clear? Is that understandable? Okay? You know, you might wonder why I'm obsessing about this, but it's actually a very important thing. It's a very important thing because, you know, when you pose yourself a system of equations, the first thing to do is to check whether the system of equations are well posed. Whether, you know, the setup is such that you should have a solution. And as soon as you have more equations than variables, the first thing you should ask yourself is how can there be solutions? Now, there are situations where you just get lucky, of course, you know, if you've made a guess, something like that. But this is not that kind of situation. You've got well-posed equations of motion, Einstein's equations, with well-posed symmetry constraint. We're not making any guesses beyond symmetry. So there have to be solutions. So it shouldn't be based on luck. So it must be that actually there are as many equations as variables. So that's the first thing to ask yourself before you start solving. That was the point of this question. And here's in a very simple context. But in more complicated contexts, when you actually are doing a research problem, it's a very important thing to keep straight. Always asking yourself, what is the structure of my problem? Okay, often a textbook would not when they're thinking of this. But of course, this is the first thing a physicist would do. You know, before you start solving, you ask, are there solutions? Okay. Okay, so this was...
this E arc peak, this off-diagonal component was computed to be identically 0.
It happened to be 0. Yeah, that's right.
It just happened to be 0. So, but still there are more equations than there are variables.
Exactly.
Even when we consider that...
Actually, in this case, one of the identities happens to be, you know, ERT is 0. So, work it out structurally, you know, without doing any calculation. This is what we can say from symmetry. Work it out structurally and then put in your specific values of ease. One of the specific values you'll put in is 0 for ERT. And check this is 0. But yes, you're right. Had you known ERT was 0 beforehand, you would have had one less concern. You would have had 3 equations and 2 variables. You would have been less concerned. Then you might worry, well, but now I've got 2 constraints. So maybe I've only got 1 equation for So, you know, you have to check. From this point of view, you will see that there are actually 2 independent equations. Okay?
So, I mean, is that a valid point of view to take, knowing beforehand that ERT is identically 0?
You can, of course. It's true. But you see, it's not following from a general principle.
Okay.
So it's a dangerous thing to do.
Okay.
The symmetry is everything here. And then the way it works out is that one of the equations happens to be 0. That now is a matter of more detail. Of course, if you think hard about it, it won't be exactly detailed. You probably will understand it, but it's a further level of sophistication to understand that. Okay.
Even we shouldn't assume anything about the functional dependence of E mu.
No, nothing. A and C. See, symmetry gave us this form, with A and C being absolutely arbitrary functions of R.
No, E mu nu, let's say, is an arbitrary function of P r theta phi.
No. This, for instance, in getting these things here, we have made certain symmetry assumptions.
Yes.
We've assumed that nothing depends on phi, for instance.
Yeah, it's theta or phi.
Theta or phi. We've assumed that there was a killing vector in T. So you must put in those assumptions.
Yeah, that this is only a function of
R. Right? So these things are unknown functions are functions only of R. That has to be put in, otherwise you'll get an inconsistency.
Yeah. Only that's what I was saying.
Yes. Okay? So you put in the symmetry assumptions you made, but nothing else.
I see.
Okay? Great. Fine. Any other questions or comments? Okay. Now most of today's class is going to be Suman, of course. Are you ready for it?
Yeah, but
I know it's not most of the class. I'm joking. But maybe just to prepare the ground for him, I'm going to revise what we were discussing. Okay. We were trying to discuss the global structure of a black hole. Okay. So we had the ds squared was equal to 1 minus beta by r dt squared plus dr squared over 1 minus beta by r plus r squared d omega 2 squared. By the way, let's add this exercise. To arbitrary dimensions. This was a black hole in 4 dimensions. We have this nice Schwarzschild, we have this derivation of the Schwarzschild geometry. When you go through what you've done, you'll find we've used d equals 4 in very few places. Okay? So generalize and find the generalization of this metric to d dimensions. You'll see that d will have to be greater than equal to 4. So let's. Okay. Shall I let out the secret? The secret is that this continues to be the answer, except that 1 by r is replaced by the harmonic form in d dimensions. The solution to del squared.
Yeah.
Del squared in d minus 1 in the spatial dimension. Del squared, whatever is the delta function. So this will just become r to the power d minus 3. Okay? So this is nice simple geometry in every dimension. Okay. Fine. But this was the metric we were studying. Everything I say basically will go through for arbitrary dimension. But I'm going to pick, just for concreteness, I'll say d equals 4. So because we happen to live there. Okay. Generalize this metric. Fine. So we had this thing. And then we had, now I need your help in what was u and what was v, please. We defined r is equal to r and t is equal to, please help me, was it u, v? Did we put a plus here? Minus. Or we did r is equal to r and t is equal to u plus integral dr 1 minus beta by r. These were the two, this gave one set of coordinates. Now let's see. So v is like t plus r. So these are ingoing coordinates. And these are outgoing coordinates. Right. So ingoing coordinates and outgoing coordinates, and more generally we had this definition of u and v, which was a v was equal to, let's just put that on the other side. So t plus, we've done this a zillion times, but I'll do it again. What was it? R plus log r minus beta by beta and a beta outside. And u was equal to t minus r minus beta log r minus beta by beta. You'll find that many books call beta 2m. Beta, many books will ignore factors of g and c squared and so on, but keep factors of 2. So, so beta is often written in a book as twice mass.
Yeah.
Okay, so just to make comparison with other people, beta is twice mass. Okay, fine. Then we did the following change of coordinates, and looking at a sort of standard reference, I see that I missed a minus sign compared to what people normally do, so I'll do that. If I've got the right, printed out the right page. The wrong page. Which one? One of them is defined. Okay, I'll just stick to what we have. And we can. One of their capital U or capital V was defined with a minus sign. So, one, do you know which one? U. Capital U. Yeah.
Whichever is with negative exponential.
Okay, great. So u was equal to e to the power minus. Can somebody remind me? U by 2 beta, and with a minus. And v was equal to e to the power minus plus v by 2 beta. Okay, what was the point of this 2 beta, the relative sign and the 2 beta? The point of that was that, you know, this term here, in the capital U and capital V coordinates, we got ds squared was equal to minus 1 minus beta by r into du dv. Help me, did I get the sign right? Yes. Plus r squared d omega 2 squared. What? 2? We can check whether it's 2 or not by going to infinity. So then it should be dt squared minus dr squared. So no 2. Because, okay, and we could check also that we got the sign right by going to infinity. So then this is, yeah, then dt squared minus dr squared with the minus sign. Perfect. Okay, so we got this, and the problem with the metric was this factor of 1 minus beta by r. This going 0 made the metric singular. More precisely, it's inverse singular at r is equal to beta. Okay, so we wanted a change of coordinates that will get rid of the fact that this was 0. And this precisely did it. Okay, this precisely did it in the following way, that if you write du dv, okay, because of this minus sign we will have a minus sign, so that will be equal to minus. Then we will have a plus from here and a minus from here, so a plus 1 by 2 beta the whole thing squared into du dv times 1 minus times now we'll write minus uv.
Yes.
Okay, times 1 minus beta by r. Have I got all the signs right? Minus 1 minus beta by r.
That minus won't be there.
This minus won't be there. Let me check. Yeah, you're probably right. All I've done is takes this guy.
No, I mean, in the metric there will minus 1 minus
There will not be. Sorry, thank you. This is correct.
I'm talking about the metric.
Correct. Okay. And then what we wanted was that this quantity reproduce the 0, so that the metric here written in terms of capital U and capital V might have some funny capital U and capital V dependence, but will not go to 0 at r is equal to capital U and capital V. Okay? And that was ensured when we chose U and V in this form, because V minus U was equal to 2 beta times this log, but then we divide by 2 beta, so we just get e to the power this log, and e to the power this log is the 0 that we have. Okay, so this was the point of the coordinate change. Now I'm just going to give you 2 minutes more grand overview of what's going to follow, and then Suman will take over. We've not yet exactly found the form of the metric in terms of capital U and capital V. We've only determined that it's not singular at r equals. We have to do a little more work to find that. Okay, that Suman will tell us how to do. Okay, and now, but just let's understand what's going on.
How did we see it's not singular at r equals beta?
It's not singular at r equals beta because the metric is completely smooth. In the sense that, okay, let me say 2 more things. First, all we've seen so far is that this factor, whatever it is, in order to get the actual metric, we're going to have to put some function of u and v times du dv. What we've seen is that this function of u and v is not equal to 0. Is not equal to 0 at r is equal to 2. Okay? Suman will show us that it's an analytic function of u and v. The main point is that it's not 0 then. Okay? But I want to emphasize 2 or 3 things. The first thing is that is this. When u and v, little u and v run from minus infinity to infinity. Exactly. Exactly. These are things you probably plan to say, but let me just to make it clear.
I have that question, but why we are restricting the capital U and capital V to be?
So let me say a few things. Okay, when little u and little v run from, so v was the ingoing coordinates, so little v was equal to minus infinity here, and little v was equal to plus infinity here. Okay, here u was equal to infinity and u was equal to minus infinity. When little u and little v ran from, let's take little v for concreteness. When little v runs from minus infinity to infinity, capital V runs from what to what? 0 to infinity. Okay? So this coordinate capital V runs from 0 to infinity, where little u and little v are both well defined. Capital V runs from 0 to infinity. Okay? And capital U also runs from, well, in this case, minus infinity to 0. Okay, now, where are these little u and little v coordinates both well defined? It's where ingoing and outgoing coordinates are well defined. So it's just in this part of the Penrose diagram, the part that is also covered by Schwarzschild coordinates. But now, the whole point is going to be, as Suman will explain to us, is that we're going to get an analytic form of the metric here. An analytic form that will have, in which we will have no problem continuing through v is equal to 0. You see, v equals 0, which was little v equals infinity, was this region. And our ingoing coordinates could not be extended beyond this. But we know that the spacetime does extend beyond this because outgoing coordinates couldn't be extended. You see, u had no trouble here, and therefore capital U had no trouble here. We go to these coordinates, or at the moment we think, okay, this only makes sense here because it has to be where little v and little u are both well defined. But we know that there's a part of spacetime here because in outgoing coordinates, we saw that part of spacetime. We know that there's a part of spacetime here because in ingoing coordinates, we saw that spacetime. So we should be able to extend to these regions. And the way these coordinates will see it is this, that from the point of view of capital V, the restriction that capital V ended at 0 is totally artificial. Maybe natural from the point of view of little v, but what was that? You know, the way we always think about these things is that when you make such a coordinate change and find this happening, it's not that your new coordinate is bad, it's the old coordinate was bad. So you see, this was the right coordinate. Then you made the coordinate change, capital V is equal to e to the power little v by 2 beta, artificially restricting capital V to run from 0 to infinity. It was a fine coordinate. Defined always. This was the right coordinate, running from minus infinity to infinity. But by making the coordinate change, capital V is equal to e to the power v by 2 beta, you force it to run from 0 to infinity. Okay, you do something so stupid, what can anyone do? Okay, you'll think that it runs from 0 to infinity, but all your formulae, your metric, will allow capital V to go through 0.
Just one thing to ask. R equals 0 is way there to the left, right, in this diagram.
R equals 0. Yes.
Right.
Suman will explain all this to us in detail. Okay. But see, look at the point. Now, this coordinate here, this ingoing coordinate, we've only taken half of its range because capital V was going from 0 to infinity, but actually it could go from minus infinity to infinity. Now, when I draw this, I'm actually drawing a conformal, tan of capital V, as again, I think you will explain to us. Okay? Because we're going to draw a conformally compactified thing, just like we did in flat space. Okay? But it's the same thing. When tan of capital V, the tan u, suppose we write tan V tilde is capital V. Then V tilde in this, because of the restriction to little v is equal to, because of the restriction of this coordinate, the restriction of capital V is greater than 0, is the restriction that V tilde runs from 0 to pi by 2. But the V tilde will actually run from minus pi by 2 to pi by 2. Because capital V can run from minus infinity to infinity.
So he runs from minus infinity to infinity means V tilde runs from 0 to small v runs from minus infinity.
Small v is irrelevant. Small v is the bad coordinate.
Okay.
Small v ran from from minus infinity to infinity. So capital V ran from 0 to infinity, you thought, but that was an artificial bad restriction. The correct range for capital V to run from is minus infinity to minus infinity.
Okay. Why is that?
Why is that? Because it can.
It can, sure. Why say correct?
Correct, because you see, suppose, well, it's clearer here in terms of, suppose somebody is going here, he hits this range, he just keeps going, nothing particular happens to him. See, we've found the question we're asking is, what is the set of coordinates in which the maximal possible region of space-time is visible? You can always, once you've got those coordinates, go to strange coordinates in which you see only part of space-time. So by correct, I mean those coordinates in which you see in a smooth way the maximal possible range of space-time.
In that sense, you can restrict some coordinates and then you can extend it to somewhere.
Yes, if you've got a space-time that solves Einstein's equations everywhere in a big set of coordinates, then you see that, okay, there's another set of coordinates in which you see only a patch of it. Clearly you have more information in the first than in the second.
Can we substantiate why the observer keeps going in this 45-degree even
Well,
after it has crossed the horizon?
Well, nothing particularly bad happens to the observer. The observer reaches here in finite time, finite proper time. What next?
We know that the observer travels in 45 degrees because it
Well, let's say not 45. Let's say he's not a light ray. He goes like this. Okay? He goes here, he reaches the horizon in finite time. And then either you need to invent a new rule for what happens at the horizon. What does the observer see when he reaches them? These coordinates end them. Okay? Either you have to supplement your rules of physics by some new rule for what happens at the horizon. which lies outside Einstein's equations. Or you notice that there was nothing particularly funny about, I mean, that if you worked in a larger set of coordinates, the observer keeps going. Notice that nothing invariant is blowing up here. No curvatures are blowing up here. How do you know that? We either know that by computation, but that's a dangerous game because, you know, computation, there's an infinite number of things that can blow up. Suppose you take the millionth del square of r mu nu alpha beta. That might blow up. Anything blowing up is so that's a dangerous game. You can't compute an infinite number of things. But what you can do is to check whether there is a coordinate system in terms of which the metric is completely smooth. If so, you know that nothing can blow up without having calculated everything. Okay? So the fact that there exists a coordinate system in terms of which everything is smooth, we've already seen this. This is the outgoing coordinates. Sorry, ingoing coordinates. Already means that there are no invariants blowing up here. It's not like anything funny is happening locally. It's not like two observers that are coming accelerate infinitely fast away from each other. It's nothing odd happening in any way.
It's only the causal structure that's...
Yeah, and as we see here, it's just that the coordinates we were using were bad. We already saw that going from Schwarzschild to outgoing, to ingoing. Right? So this experiment we could already describe in ingoing coordinates. We get answers to any question you ask. Seems perfectly okay. And then from that point of view, we already have this idea that, you see, the ingoing coordinate for this region of space-time, the ingoing coordinates were the good ones. What you then make a coordinate change from ingoing coordinates to Schwarzschild coordinates. That makes this region of space-time back to Schwarzschild, but those coordinates are unsuited to this region of space-time. All right, it's like, you know, you've got a region of flat space, and you decide to use the coordinate x is equal to log r minus 1. You can do that, nobody can stop you, except you won't be able to describe r less than 1 in that coordinate.
So I have a question. So two related questions. So first is how do you know that this is the maximal atlas for the Schwarzschild spacetime? And then given a general spacetime, how do we construct the maximal atlas?
Yes, we know that it's the maximum atlas because it's geodesically complete. Okay, I'll explain what that means. Let me finish just saying roughly, sketching out this thing, then I'll explain the answer to this question. Okay, let me finish, yeah. Okay, see. So now what we have, so I'm just basically sketching around on all details Suman will tell us. But now we have this u and v coordinate. Then we'll do the same trick we did. That is, we will say u is equal to tan of u tilde and v is equal to tan of v tilde. Okay? So naively, our u tilde and v tilde will run from u and v run from minus infinity to infinity. That's our postulate. Okay? Therefore, u tilde and v tilde run from minus pi by 2 to pi by 2. So, just like before, we have a diamond in u tilde v tilde space. Okay? Just like before, we have a diamond in u tilde v tilde space, minus pi by 2 to pi by 2, minus pi by 2 to pi by 2. You know this, it's like the blue and red or whatever lines we drew last time. You understand, right? Suman will do that more carefully. So, this looks like the structure of a Penrose diagram. Okay? However, there are two issues. The first is we have not been careful about where r is equal to 0 lies on this time. Why is that important? It's because r is equal to 0 represents a genuine curvature singularity of our metric. How can you check that? You can check that by computing r mu nu alpha beta at r equals 0. You'll find something that grows like some power of 1 by. You see the reverse, the logic. You can never prove a spacetime is is smooth by computing a finite number of curvature invariants. But you compute one that blows up and you check that it's not smooth. Okay? So somebody might have said, well, how do you know? If you try hard enough, you can't find a coordinate system that goes past r equals 0. Well, I know because I've computed something invariant and it does. Okay? So if you want to prove something is smooth, you have to find a good coordinate system. You want to prove it's not smooth, you've got a simpler task in your hand.
But if we don't use the extended space coordinate system to compute the invariant quantity, and if we are restricted to some region, and we have seen that the invariant quantity is not blowing up or that.
Yeah, so all you've done then is to say that the invariant quantity doesn't blow up here, which is true. But that's not the question you're asking.
Yes.
You're asking, does it blow up here?
Yeah, that's why we have to choose also the right coordinate system to calculate.
You have to choose a coordinate system that takes you to the point that is good near the point which you are investigating. See, I've got a manifold. If you've covered it in patches here and here and here, clearly you can't ask about this point using this patch.
Yeah.
Because it doesn't cover the point. You have to be in coordinates that access the patch. That is clear. But you say r is equal to 0 in polar coordinates is accessed by by polar coordinates. It's a singular place in those coordinates, but it's not singular in the manifold. That's very much like the event horizon. Okay? How would we prove that r is equal to 0 is not singular on the manifold? By making a coordinate change, in this case going to Cartesian coordinates. Okay? No amount of computing curvatures and checking that that was non-zero would completely establish that it was non-singular. On the other hand, if we had a genuine singularity near r equals 0, let's say some other metric, which I won't give you examples, we could write on many, just checking one thing is blowing up, one invariant thing is blowing up, is sufficient. As you say, you have to of course be in coordinates to access that point. But once you access that point, you can reliably compute at that point, doesn't matter which coordinate system you use, because it's an invariant. Okay? So, what we have forgotten here is where r is equal to 0 lies. Now, r is equal to 0 we cannot go beyond because it's genuinely singular point. So, we need to plot where r is equal to 0 lies on this diagram. And I think Suman will do this for us, and he'll find, if I remember right, precisely midway between these two lines. And we know that because this happened at v is equal to infinity, minus infinity, which was capital B is equal to 0, which was v tilde was equal to 0. So it's precisely halfway between this. That I did for u tilde. What? Yes. I'm saying that there are these two lines. Without doing a calculation, you don't know the shape of these lines, but you know where they hit the edges.
Zeros.
What? They hit the edges at v equals minus infinity, which was capital, yes, which is exactly halfway between this. Okay, so we've got a diamond, and then halfway between we've got these points. Turns out that these lines just go straight. Okay, now anything that goes, you've got an observer, anything going beyond here is not there. So although you started with a diamond, this is removed, and this is removed. But I'll draw them with dots, just so that we can keep our coordinates in mind. They're not really there. Okay? Now we can ask, what's what? By which I mean, which regions of this space-time have what values of capital U and V? I just mean, what we're interested in is where is it positive, where is it negative. This capital U being negative is irritating because it throws me off. I always do it the other way. But anyway, let's be standard. So firstly, I'm going to draw these 45-degree lines. Why are these 45-degree lines important? These 45-degree lines are, this was little v equals minus infinity, and therefore capital V is equal to 0. And this was little u is equal to infinity, and therefore capital U is equal to 0. Okay? Now here what do we have? Here we have u is equal to minus negative, and v is equal to positive. But v switches sign here. So we have u is equal to minus and v is equal to plus. Here V doesn't switch sign, but U does. So we have V is equal to positive and U is equal to positive. V is minus, yes. V, yes, thank you. U is minus V and V is minus V. Thank you. Okay? And here both have switched signs compared to here. So U is equal to positive and V is equal to negative. This already shows you that there is a new region in the spacetime that is not accessed either by the ingoing or by the outgoing coordinates. From the point of view of capital U and V, it's obvious. Because since capital U and V can both run over positive and negative values, what was the ingoing region? It was the region where capital U switched sign, V didn't. This region was the region where capital V switched sign, but U didn't. But there's also another region where both switched sign. That's this. Turns out that the full metric is complete symmetry between interchange of this and this. Just two asymptotic regions. Okay? And this is the full Penrose diagram of the maximally extended Schwarzschild geometry. Any general questions or comments, ask me now, and then I'll hand over to you. Geodesic. Thank you. Now, how do you know that this isn't further extended? Consider any geodesic in this diagram. Okay? Every geodesic in this diagram either ends at a singularity or ends at these things. So now you can ask, how do I know I cannot? Well, beyond singularities, we give up. Okay, that's the role of quantum gravity. Okay, classical gravity should work at singularities. Fine. What is the only possibility is that you can analytically continue beyond here. But is that physical? To ask that, we can ask, does any observer reach one of these places in finite time? If that doesn't happen, if you can continue it, that's an issue between you and God. I mean, it's not for observers. Finite proper time. Okay? What is the mathematical version of that statement? The mathematical version of that statement is, well, one way of saying it is just what we said. Is there any line that reaches this point in finite proper time? Now, this sounds good, except it's not very precise in this case. Because these things here are places where only null rays reach. Any real geodesic reaches here. Any time-like geodesic reaches. So first question you can ask is, do time-like geodesics ever reach this point in finite proper time? Easy to show that it's no, because this point is t equals infinity, so come on. Okay, okay, you can easily check that. Okay, but we want to know, can you continue beyond here? That's a more tricky question to ask. And the way that general relativists pose it is to ask, what is the analog of proper time for null rays? It's affine, this affine coordinate. So are there null geodesics that reach this point in finite affine time?
What's affine time?
Affine time was the analog of tau for the null geodesic. Do you remember in a class we wrote down the geodesic equation by deriving it from the form of from the action which didn't have the square root?
Right.
In that form of the action, we could take m equals 0
Right.
nicely, and we retained the ability to write down the geodesic equation in a particularly distinguished coordinate system.
Okay.
We used the coordinate tau, which was really genuinely proper time,
Right.
for the time-like case. But then just taking the limit m goes to 0, we got the form of the geodesic equation in a coordinate along the geodesic that was just the continuation of that. This is the affine parameter. Okay, it's the parameter in terms of which the geodesic equation retains its standard simple form. Okay, you can make a coordinate parameter change along that geodesic, and that's fine, the equation will become more complicated. There's a distinguished parameterization of every null geodesic. Just like proper time was the distinguished parameterization of every time-like geodesic. You don't need to use that to use any coordinate. There's a similarly distinguished parameterization of null geodesics, the one we basically worked with. Okay, which is called the affine parameter. And it's the analogous question. It's the analogous question for null light rays. Okay, it is the question. It will turn out to be the following question: that if you send, if you send a pulse of light, you can ask how many wavelengths. How many times will it oscillate? It says before it reaches that point. That will be infinity. Okay, so it's the analogous question to reaching a finite proper time. The point is that in all these diagrams, all null geodesics or proper geodesics that reach any edge of this diagram reach them in infinite either proper time or affine parameter. Okay, when that happens, we declare from the point of view of physics that our job is complete, because nothing physical can reach the boundary in finite time. That's roughly the idea. Okay, now always these declarations are a bit, maybe that somebody will find a way of finding a bigger space, and that might be useful for some purpose. Okay, so the declaration has to be taken for what it is. Just a statement that this is what we decided to do, that if we, it's like infinity it's sort of like a space, like for Euclidean space, something's at infinite distance. It has a quote unquote boundary, but at infinite distance, we say that's okay. We'll never reach that. That's the point. Okay?
So for instance, in Reisman-Nordstrom, when you
yes.
have this series of such diagrams sewn together,
yes.
and which would mean that in some, if we consider only this part of the Penrose diagram,
that would be geodesically incomplete in that case. You would be able to find geodesics that would go and hit some edge of that diagram at finite affine time, and that's not acceptable. Okay, in that case, you'd even be able to find a finite proper time for time-like geodesics. Okay, so then it's clearly not enough, because it's not answering questions that you can ask experimentally. What if this guy is moving in his rocket? What will he see? If there's a boundary such that you never pose such a paradoxical, you can't pose such a question that you cannot answer, then you will say, okay. Okay, is this clear? Any other question?
I haven't understood this extended part. I'm sorry.
Which extended part?
If it is extended, then
if it's you cannot extend this further by my rules. However, when you look at charged black holes, and this is what Upman was talking about, there is a more complicated causal structure, which we will discuss at some point in the course. Okay, at the moment we're looking at the first simple case. More complicated causal structure also for rotating black holes. There's an interesting game. Yeah. Okay. All these, with luck, we will discuss in the course. All these things we will discuss. We have two bread and butter things left. That is to discuss basic cosmology and basic gravitational wave physics, and then we will try to have some fun. We'll do various interesting things. But let's finish the bread and butter stuff first. This is our first pass on black hole physics. Okay. Yeah. Any other questions? Any other questions?
Is the coordinate R well defined in the left region?
Is the coordinate R well defined in the left region? Yeah. So now R will be defined by an equation that tells you what it is in terms of U and V. And that will be well defined. Okay? I'll say it roughly, and Suman will give us details. Roughly, you see, what was coordinated R in terms of U and V? It was, V minus U is equal to whatever, 2R plus beta log. But now this U minus V minus VU we can write in terms of capital U and capital V. And then you think of R as being defined implicitly by this equation. Okay? And then you can ask, does this have solutions? Everywhere. Okay? And Does this have solutions everywhere? Now let's see.
It's 2r plus 2 beta.
2 beta, okay. Yeah. Now let me see. You see, the only way it would not have solutions is if there was some sign for the left hand side for which this was not well defined. Okay? But you see, and it's true that r runs from 0 to infinity. So had this not been there, there would have been a sign for the left hand side for which this was not well defined. But this log here runs from minus infinity to infinity. So there's no real issue.
So any r equal constant surface would be two-sheeted.
Exactly. In fact, the sheets run like this. R is equal to infinity goes here, larger r goes like this, and smaller r's go like this. Okay, so r is equal to beta is this. Okay, so r is equal to beta, for instance, would be something like this. R is equal to half beta would be something like this. R is equal to beta would be something like this. Two vertical lines. Not real significance, no real significance to a vertical lines. Notice that there is great significance to these two things. Okay, that I will talk about. I will talk about the significance of that after someone gives us a little algebra. Come, I've taken too much of his time. I hope, by the way, you guys don't mind me asking you guys to come to the board once in a while. I think it's useful because it keeps you guys engaged. It's just some simple things, but so that you're not just following like on auto mode.
So up to a constant, it is u into v. So it is e to the power v minus u by 2 in dependencies in the coordinates. These are just constant. And so, okay.
Wait, are you going to start with the actual metric and tell us the form in capital U and capital V?
Yes. So du dv is, so it is v minus u is r star. Or r star is r plus the whole code.
It's twice of
Twice
r.
r star. Yes, by 2. So beta is so du dv is equal to r star by beta. If you take u by 2 beta, if you scale this u by 2 beta, then this constant will go on. That is, take just u by 2 beta and v by 2 beta. So now here is a factor in the matrix, that is 1 minus beta by r. And e to the power minus r star by beta is equal to 4 minus, so minus 1 by beta r plus beta ln r minus beta by beta is equal to minus r by beta into
There was a mod.
This is
one minus beta by r factor.
But if r greater than beta,
r greater than
yeah, there will be a overall signature with r minus beta.
Yeah, if someone clear parts of the board and write, more
Yeah.
systematically, if you don't mind. Why don't you make an algebraic claim first, and then we can check it. What does the metric? What does the metric become in capital U, capital V coordinates? And then.
So dsa square is 1 minus beta by r that is the coordinate. And now I want to calculate from these two relations dV is equal to e to the power v minus q by 2 beta.
What's the claim? Is that the claim?
No, he's going to make a.
calculate the metric in terms of capital U, capital V.
He's going to give us the claims.
That's a good one. What about this?
He's changed his definition of.
I have changed
Oh,
this to
Yeah.
scale this
I
by
see.
2 beta.
Okay.
4 beta square.
Yeah, yes, he has changed.
He's changed the definition of U and V.
And there will be another minus beta.
That's fine. Yeah. So now you want to write d little u, d little b in terms of capital D,
Capital U, capital V.
capital V.
Yeah.
So the logical equation is d little u, d little v is equal to e to the power minus r star by beta.
Yeah, so e to the power minus r star by beta capital U, d capital V.
Right.
So it is equal to e to the power minus 1 by beta to r plus so beta ln of r minus beta by beta.
Right.
Then it is e to the power minus r by beta into beta by r minus beta because there is a negative sign outside. Okay. Now you take a common r and the beta. Then it will be 1. So 1 by 1 minus beta by r.
Great. Great. And therefore minus du dv into 1 minus beta by r.
Yes. So small u dv into 1 minus beta by r is equal to minus beta e to the power beta by r equal minus beta plus r square and calculated from this equation. I am not written the equation. The equation is v minus u is equal to 2r and substitute u and v by ln of u. So from this metric it is clear that the r coordinate is previous r is equal the radial coordinate. So at r is equal to beta it is smooth. So in this
This is
coordinate
r greater than 0. R greater than beta.
No, it's for lower R's.
it is also at r is equal to beta.
R greater than equal to beta.
Equal to beta. So beta includes this.
No, I am saying that how do you incorporate the mod thing here?
There should be a signature. I have put a signature here for this. See, I think the signature flips in if we go inside the region. So there should be in principle plus minus beta, where r greater than beta or r less than beta.
Sorry, I didn't understand. Say that again.
Actually, 1 minus beta by r is equal to, I have done this in this way, beta by r into signature of whether r greater than beta or r less than beta. I don't know whether it is right or not. Maybe my negative sign is there, but there should be a relative sign in this factor. And if we want to cancel this mod with this factor, then this signature will come.
Wait, why are you putting a mod?
If we actually, I have done it, but it is not there. But if we want to get the right coordinate system, now if we want to, let's say, write x, the final coordinate in terms of small x, there is a r by 2 beta, r by beta minus 1 to the power half, and it is not defined as a square root.
What is final x? What is that?
Actually, 5 mod beta.
What he means is whenever we take logarithms or square roots,
Logarithms of
there has to
negative
come.
is not defined. That's why
So
One
this
has
means
to
that
be
u and v covers all the region.
minus infinity plus infinity.
Nee,
Oh, all the
all the
regions.
space, even inside the black holes. But
But I think they are degenerate.
no, means if I put mod, then r can be less than beta.
Actually, we could have made the transformation from capital U and V to r theta directly. We could just bypass small u and small v.
Right.
Then we'd have things like e raised to
Right.
r.
Right. Why don't you write down the equation that defines r in terms of capital U and capital V?
Capital U and capital V
Yes.
in terms of R. Okay, so
Please, write it where we can see it.
Yeah.
Oh, that's it.
R
No, now write capital V and you take up the right product that you want. You want to cancel the t business.
yeah. So plus minus will be cancelled. So capital U into U into P is equal to the power. The 2 will be cancelled. By beta into plus. The same thing. U will be
No, please write it. Complete it.
okay.
And put the minus sign. There's a minus sign overall outside. Okay. Now expand the log.
Expand log means
E to the power log is it's r minus beta by beta.
E raised to the r by beta. Yeah, sure.
This is your equation, right?
yeah.
Now where is any mod? There's no mod.
You can easily put mod there.
There's no, all that is, we're working some bad coordinates. This is your final relationship. You see, you don't want mods because you want R to be an analytic function of U and V.
Yes.
You put a mod, it's not going to be analytic.
Okay. Yeah.
This is your relation. There's no mod. The mod was, this is the equation that defines R.
Basically, small u and small u only covers the region where is r.
Exactly.
So you can't use partial coordinates when r is less than beta.
You can't, really speaking, you can't. Yes. You can see that, right? Because the metric degenerates at R equals beta. How do you go through it?
Okay.
If you don't mind, someone keep that on the board, that last equation on the board. It's useful to have.
One question here.
Just write that equation before you ask.
When we calculate
raised to the-
curvature invariant, we should use some other coordinates, not the Schwarzschild coordinates.
Well, in principle, you get the right answer. You say the Schwarzschild coordinates bad once, but you should. let's use ingoing coordinates. It's safe. It's as easy and safe. You won't make a difference. Okay, now go on. What was your question?
If I want to calculate this u only, and that is e to the power t by 2 beta.
See the problem.
R
Yeah,
minus beta to the power.
that's not the way you think of it.
Okay, okay,
Okay,
okay.
this is your final answer.
Yeah.
Now you've forgotten about everything else.
And
Capital U and capital V
Is
are your
new
coordinates.
coordinates.
You're not calculating them.
yeah.
They're coordinates. What you have to calculate is R. You calculate it by solving this equation. Right? This was the right answer. Everything else was because you did strange coordinate transformations on the good answer.
Now we have to do u is equal to tan integral into u is equal to this factor will remain same
We got it.
and there will be a beta by beta. So
Right.
now we will take this part only. We will remove this cos square factors, and it is the same code. It is same as the previous one. Conformity. So the new thing but the range now becomes finite by this tan and u tilde from minus pi by 2 to pi by 2 and v tilde also.
Good.
But v minus u is greater than r is greater than 0. I think I should do from this.
Yes.
Yes. Yeah. So r is greater than 0 means this does not give anything, but uv changes signature in below beta and greater than beta.
Yes, true. That's what we saw, right? That u and v are flipping sign as you go past it. Why don't you draw the?
Relative signs flip.
Have you finished writing your metric firstly?
Yeah.
You're not going to take it out and show us what you get. What happened to the r square term?
R square will be multiplied by cos square u tilde cos square v tilde.
Wait, finish writing. Write something with a factor outside, so you know. And write the factor outside as well. ds squared is 1 by cos squared u cos.
Okay.
And then you're going to discard this factor and work with the conformally
Yes.
equivalent metric, which is this. Clear the right hand side of the board. Clear all this. Clear that part if you don't mind. Anything. Excellent.
There is a beta square term in this first
product should have 2 beta whole square. Yes. That will be-
Yes.
yeah.
That is. So now, what is the coordinates? T plus r is P is x plus t. P is t plus r. So
Actually, sorry to be nitpicky, but if that's the case, then u is going to be twice of beta plus times tan of u tilde. You rescale once, you rescale. You define u and v as tans, right? Because these are dimensionless. So u has to be twice of beta times tan of u tilde, right? And v has to be twice of beta times tan of
no, no. You may have dimension of 2 beta. You can take it to
U is
the-
equal to tan u theta. That's what we wrote there.
Yeah.
U has dimension of length.
u has dimension of beta, right? U is not dimension of beta.
Yeah.
It's u by 2 beta.
So 4 beta square will be there.
Then if we are.
So in this coordinate, by 2. By 4. Yeah. Now, I have to write down the coordinates.
You want to show us the range of,
Yes.
that's the most important remaining thing.
Utilize t minus x by t. So u is equal to tan of t minus x by 2 and
U by 2 beta is tan of t minus x by 2?
I should also have taken a
Why? U tilde, v tilde were dimensionless quantities.
that's why
We want x and t to have a dimension.
Okay, up to you. But I thought you wanted x and t to have some range 0 pi, that kind of thing.
yeah.
So don't, yeah.
So, so from this relation,
The 2 betas will cancel. Because u by 2 beta is tan, right?
sorry,
You'll write, you want to write it in terms of the tans, right? Or not?
yes,
So u by 2 beta.
Okay, u by 2 beta is u tilde.
Yeah.
So u by 2 beta is tan u tilde. Tan u tilde is this.
Good.
So r is equal to 0 means there is minus. Yes. R is equal to 0 means is equal to 1 means so minus x is equal to pi minus t minus x.
Plus x. One of them is no. One of them is plus x. Oh, you. Oh, sorry.
Yes.
Meant.
So t is pi by 2.
Excellent.
So if we draw the coordinate system as t and x, the t is equal to pi by 2 line is this,
Well, it's that or shifted by pi.
or shifted by pi. This also. So these are the singular points. So r is equal to 0 represents these two lines. And I will do r is equal to beta means it is simple that t is plus minus x because this is 0 and r is equal to beta. Then either of this is
Either u or v is 0.
so you will get these two lines. And the other range is set by u minus v. And previously we have seen that how we have to do this.
Yeah.
But this is pi by 2 and this is also pi by 2. This is minus pi by 2. And similarly for this case also. Yes.
Perfect.
So these are the beta lines, I is equal to beta lines.
Perfect. Questions for someone?
Pi by 2, what is pi by 2 there? X is pi by 2?
A capital T.
T, capital T, this T coordinate
On the right.
on the right.
There, in the diagram. The right.
This capital X.
Capital X is pi there.
Yeah, I have thought also that because this should be
Yeah.
symmetric.
Perfect. Perfect. That was great, Suman. Any questions? More questions? Great. Thank you very much. That was great. Okay. Any questions, clarifications about this really nice presentation?
Why do we take u tilde and v tilde going from minus pi by 2 to pi by 2? Because they're tan inverses of exponentials.
That's the point. Your tan inverses of exponentials when you express it in
Bad coordinates.
little bad coordinates. These are coordinates in their own right. Okay? This is always the point. This is always the point. You cannot go from bad coordinates to good coordinates without making a coordinate transformation that you think of as suspicious. But the bad thing was in the inverse, not in what you're doing. Okay, great. So, we've 1 o'clock. I thought today was going to be cosmology. No, okay. Okay, let's see where we can go.
Could you keep the right side percentage?
Sure. Excellent. Now, I just want to say 3-4 more things about this, because this is very important, at least for a certain kind of physics. I want to say a little more about this Penrose diagram. Okay. Every line drawn in this Penrose diagram has significance. Okay, this is what's called the future singularity. This is the past singularity. This line, from the point of view, this line is Scri plus and Scri minus, and then there are the mirror images of that on the other side. We've already talked about that. That has the same significance as in flat space. The lines that had no analog in flat space are these two lines. They're clearly sort of significant lines, and let's explore their significance. Okay. I'm going to view everything from the point of view of the observer at this side. Okay, if you're a physicist here, and you do. There's a mirror universe here, which we shouldn't take too seriously. I'll tell you why. You shouldn't take too seriously, because a black hole that is formed by collapse has a Penrose diagram that is only one part of this. We'll discuss that. Okay, so if this describes a black hole that existed forever. Okay, but in a universe, if we assume that our universe started without black hole formed from collapse, then the causal diagram will not include these parts. Okay, I'll show you in a bit what it would include.
Does it mean that it's not possible to cross over from this side to that side in finite time for an actual thing?
This is also true. This is also true, and we'll see that in 2 minutes. But that's a separate issue. There are two different questions. Is it that there are two parts of the universe that we cannot communicate with, or is it just that it's not there? Okay, and black holes formed from collapse, it's just not there. Okay, we were looking at the maximal analytic continuation of space-time for a black hole that has existed forever. If you put in the fact that the black hole formed at some time, then that changes this. Okay, so for the black hole at the center of the galaxy, or for the black holes that collided in LIGO's experiment, presumably, these regions were not there. They just were not there. Okay, so however, anyway, at the moment we're looking at this model space-time, we're analyzing it, taking it seriously in its own right. There are theoretical systems in physics in which the whole diagram plays a role. Whole diagram plays an important role. So this black hole is called the eternal black hole. And in the context of what's called the ADS-CFT correspondence, we sometimes, for a theoretical purpose, namely to study a field theory at finite temperature, need the actual eternal diagram with both sides. So the solution exists, can be taken, studied in its own right as a conceptual solution of general relativity. Whether or not it corresponds to a particular, that's a separate matter.
For thermophiles?
Yes, for the thermophiles, exactly. Okay, so right now what we're going to do is to carefully look at the significance of these lines. From this diagram, the significance of these lines becomes absolutely clear. And it's totally obvious, but let's say it once. What is the good thing about the diagram like this? It tells you about causal relations. What does that mean? You see, suppose you've got an observer here. He and his friend is so we've got two observers, let's call them, I don't know, Amit and Anil. Okay, okay, so Amit is here, Anil is here. Amit is an explorer, he decides to go and look at what happens before, and they decide to meet next day for dinner. Okay, so Amit goes here, Anil continues here, and then he waits and he waits and he waits, and Amit never comes back. It's not because he doesn't want to keep the appointment, because once he's got here, there's no way he can make it back. Okay, this region of space-time, the region from which no observer and no causal signal, no light ray, can ever make it out back into here. That's manifest in this diagram. You see, it's a beautiful way of drawing it, because nothing can go more than 45 degrees. That's the point in this diagram. Okay? What is the future of Anil? Well, he sort of sees bad things in his future and tries to accelerate away. He's got the newest turbojet rocket, so he goes almost to the speed of light. Can't help it. He bangs into it. Okay, the future is the singularity. Exercise. Check using ingoing Eddington. Check using ingoing coordinates. That a geodesic falling at constant angle, a time like, at constant theta and phi hits r is equal to 0 infinite. We had this?
Yes.
I'm sorry. Infinite proper time.
Yeah.
That was it. I'm sorry.
Yeah, I mean, you have a problem in which you ask us to derive the
Maximum time, yes. Thank you. I forgot that, yes. Okay, right. So the point is that this Anil is going to hit the singularity and not live very long because he's got a finite life. Now, had Amit and Anil been separated here and Anil had gone here and he wanted to come meet his dinner point, he could have done that. So what is the significance of this line? It is the line that separates these two possibilities. Anything that happens here is causally disconnected from anything that happens here. Do you understand? No matter what's going on here, classically in general relativity, an observer here who stays there for the rest of his life can never know. Okay? In particular, Scry plus never receives signals from anything that goes on here. Okay? This line that separates points that can communicate with Scry plus from those that cannot has a name. It's called the event horizon. Okay? So this line here is called the event horizon. Technically, in this diagram, it's called the future event horizon. This is to distinguish it from another line that plays a sort of symmetric role, but it's much less physical for physical black holes. What is the role of this line? This line separates points that are causally related to Scry minus from those that are not. If you have someone here, he could have come from either here or from here. On the other hand, if you have someone or something here, he could only in his past have come from or received signals from the singularity. It's the mirror image of what we said, except past is going to future, Scry plus going to Scry minus. It's just turning the diagram round on its head. Okay? This is much less physical for physical astrophysical black holes. This region does not exist. This, as far as we understand, is physical for actual physical black holes. There is a real surface beyond which once you go, you can never communicate to Scry plus. Communicate with Scry plus, yes?
Can you say any event that in that event some particles is created from this lower singularity and it comes in the real world?
In the real world, you see, in the real world, as far as we understand, there is no lower singularity. Okay? There is a sense in which cosmology, some scenarios of cosmology look like this, where this is not too dissimilar from, in some scenarios of cosmology, from the Big Bang. We'll discuss that. Okay? But when we're talking about black holes, like black hole at the center of the galaxy, or black holes, Cygnus something or the other, 27X349, whatever they okay? This part does not exist for those black holes.
Because those are formed from the...
I'll tell you, we'll study it in detail later on, but I'll tell you what the Penrose diagram for a collapsing black hole looks like. I'll just draw it for you. Now that you guys have got used to Penrose diagrams, you understand what it means, even if we don't derive it, right? Okay, remember that the Penrose diagram for flat space was this. Now, the Penrose diagram for a collapsing black hole is simple. It's just a part of this diagram where this part is removed and becomes the singularity. Something collapses to form, and this becomes the Penrose diagram. What does this mean? It means that there is no point that had its origin anywhere but time like minus infinity or square minus. However, there are points in the future which have their future only in the singular. So, it's just a part of this diagram. But yeah, how would you say it? It's like extending this here and cutting it off here, something like that. Okay. It requires some actual. We'll study this if we have the time. We'll study the Oppenheimer-Snyder model of collapse, dust collapse. It's a beautiful analytic solution for black hole formation, done by Oppenheimer and Snyder, 1930s or 40s. When I was a student, I did my VSRP here. I studied that solution, and it's a beautiful solution. Okay, it really shows the formation of this black hole with this future event horizon forming, no past horizon. So black holes forming from collapse behave like this. Okay, so for astrophysical black holes, this is the only part of the Penrose diagram you should ask questions about. It's the only part that exists. For other purposes, you may ask other questions. Okay, fine. So this is the future event horizon, the past event horizon. Then there's all this stuff at the other side of the universe, which we'll talk less about until we have a context to talk about it. Okay. By the way, notice that this diagram does not show any other side of the universe. It doesn't exist. It's not like collapse creates a whole new universe. That would be absurd.
So in this case, and all time-like geodesics, they would all lead into the singularity eventually.
Or no, they could also go here.
Okay.
Think physically. If you stood outside the black hole and resolved always to stay there, you'll never go into the black hole. Okay? This point looks like it's part of the singularity, but it's not. Right? This is the analog of this point in the flat space Penrose diagram. And it exists in this diagram, distinct from the singularity. Okay? Great.
So that point is the intersection of the scribe plus and the singularity.
Exactly.
So what, and that specific, I can understand two sides of that one, but what does that point specifically mean?
It is the point at which a time-like observer who's not sucked into the black hole will eventually end up at. He doesn't end up at scribe plus because he's time-like. Only light waves end up at scribe plus. Doesn't end up in the black hole because it doesn't go into the black hole. Okay? Excellent. Now, I want to give you some generalities, and we'll see what we can do in the course. Okay, we could see. It would be very nice to talk about the laws of black hole mechanics and to understand what I'm saying now in mathematical terms, and we'll try. Let's see how fast we can get through cosmology, gravitational waves. We'll see what we can do. Okay, but at this point, I'm just going to tell you in words. Here, see, so far we've looked at one solution of general relativity that has this property. Namely, it has an interesting submanifold that separates points that can communicate with scribe plus from those that cannot. More general solutions of general, this is a baby solution, right? It's a solution in which nothing's happening. Something's been there forever. It's not. More general solutions of general relativity, in which things happen, also have this general property. You can imagine that there are some points in space-time such that from that point, no time-like or null future-directed world line ever reaches scribe plus. Okay? If that's the case, there is a boundary between those points that can make it to square plus and those points that cannot. That boundary is codimension 1. Because all boundaries are codimensional. Okay? So this space, this surface, the boundary of this surface, of these two regions, is for general space-time called the event horizon. So the notion of an event horizon is more general than for this particular solution. Okay? Some space-times can have event horizons, even though they're not the solution. Okay? And in general, an event horizon is a causal boundary. Now, you see, why are you on an event horizon? You're on an event horizon because points here can communicate with square plus, but points there cannot. As you move towards the event horizon, you're finding it harder and harder to communicate with square plus, which means that the light rays that you send out reach square plus later and later. Exactly on the event horizon, it never reaches. So, but what happens to the light ray? You know, you had a light ray that was going to make it out to square plus, and then you move it a little bit, and so you've gone to the event horizon. What happens? The light ray continues to exist. It never reaches. It doesn't make it out to the singularity. It doesn't make it out to square plus. It just stays on the event horizon.
And it definitely does not reach the future time like infinity.
Either.
Although the point ends over there.
Yeah, that's a strange point, that one point.
Yeah.
So what have we realized? What we've realized is that that the event horizon has light rays moving on it. In fact, it's a general result that the event horizon can be foliated by congruence of light rays. Just like any space-time. Do you remember in our derivation of the geodesic deviation equation, we had these time like geodesics, a congruence of time like geodesics that filled out all of space-time. The event horizon is a special place. It's a codimension 1 manifold which is composed of a codimension 1 congruence of null geodesics. These are the light rays that are trying to make it out to infinity, but never manage. Okay?
They'll just rotate around the surface.
They'll just rotate around the surface or just go radially outwards along the surface. You see, if you're trying to make it out to infinity, you don't want to rotate because you're wasting some of your speed. Suppose you're in a tough potential and you want to get out to infinity, you go run as fast as you can. Which direction do you run? You run outwards. That's what the light rays will try to do. Okay? They stay at r is equal to 0. Sorry, r equals beta. R is equal to beta. R is equal to beta is a big place. It's this place. That's what they do. You see, you know they're staying at r equals beta because this whole line was r equals beta.
But it seems like even the velocities are tangent to the submanifold also.
The velocities are no. What does that statement mean?
The velocities.
The light ray moves in the direction of the.
Yeah, I mean it stays on the submanifold.
It stays on the submanifold. Exactly. That's why the submanifold is generated by this congruence of light rays.
It's both normal and tangent.
Exactly. Now, the second property of this, which is related to the first property, is that this event horizon is always what's called a null manifold, a null submanifold, which means that the normal vector to this manifold is null, and which is consistent with the claim that the normal vector to this manifold actually lies on the manifold.
How do we know the normal is null?
We know. I haven't told you all the reasoning. Okay. I'm just giving you a bunch of facts. We'll have to do this more carefully. Okay. However, I'm making some claims. The claim is that these distinguished geodesics. Okay. Consider a manifold. Let's start this way. Consider a submanifold which is null. Okay. So suppose I've got a submanifold. I call it M. This is the manifold f of x is equal to 0. Okay? The manifold is null, which means that del mu of f, okay, del mu of f is a null vector. Okay. Now we've got this normal vector that is null. What does it mean? The normal vector is the vector that is tangent, the set of infinitesimal tangent vectors on the manifold are those tangent vectors that are normal to the normal vector, by definition. Consider a point on the manifold. Look at tangent vectors. So at that point there are tangent vectors in all of space-time. But there's a distinguished set of tangent vectors that lie on the manifold. That's what defines the manifold, patch by patch. Okay. How do you characterize these tangent vectors? Well, they're the tangent vectors that are orthogonal to the normal. Okay? But we've already found one tangent vector, one vector that is orthogonal to the normal. That's the normal itself. So in particular, the normal itself lies on the manifold. Okay? So this is a manifold now where the normal vector lies on the manifold. Okay? Therefore, the equation dx mu, let me call this whole thing with some suitable normalization, won't matter very much. Dx mu by d lambda is equal to n mu is a well-defined equation that gives you integral curves on the manifold. Do you understand? N mu is a well-defined vector field on the manifold. And this equation defines a set of curves on the manifold. How does it define it? Well, you're at a point on the manifold. How do you move? In the n mu direction. Then how do you move? In the new n mu direction, and so on. This defines clearly a d minus 2 parameter set of curves. Why d minus 2? Event horizon itself, or the null manifold itself, was d minus 1 dimension. Okay? But that gives you, it's foliated by a d minus 2 set of curves. Clearly these are null curves. Shall I give you an exercise now? Why not? Okay. I'm not sure. Later, when we study it more. These are null curves, and you can prove that these curves are always. Let's do it. Check that that the curves so generated are GD6.
The normal vectors lying on the submanifold itself, but there's no real distinction between normal vectors and tangent vectors to the submanifold anymore.
Wait. The space of tangent vectors is d minus 2 dimensional, but at any given point there's exactly one normal vector. The normal vector is a very special vector in the submanifold.
Even the space is one dimensional. The space of normal vectors is one dimensional.
Yeah, okay, you can multiply it by any number if that's what you mean. Okay, so this equation here, okay, generates a set of null GOD6. Okay, so you generate a congruence of null GOD6 by this equation. So you've got this manifold, this null manifold, where along the null manifolds there's this congruence of null GODs. These have the physical interpretation of the light rays that are trying their best to get out to infinity but never make it. Okay, so there is this, you can imagine that there are actually light rays stuck there. Somebody in the far past tried to make it out. Okay, separating points from those points that can make it that are causally connected to sky plus from those points that cannot. Okay, so this is the structure of the event horizon of a general spacetime. And what's sort of incredible is that this event horizon has many interesting properties. Something that we will study, if we have the time, is a remarkable theorem starting with Raychaudhuri and ending with Hawking. Okay, which says that you can define an area of this event I won't give you any details now. You define an area of this event horizon. And the theorem says that the area of a future event horizon always increases in time. Okay. More precisely, the area enclosed between any, carried by any set of geodesics, even that little infinitesimal area always increases in time. Okay. And this remarkable geometrical property of Einstein's equations has an interpretation in terms of the second law of thermodynamics. And the connection comes about because we believe that there is a close connection between the area of the event horizon of a black hole and its entropy. And so the second law of thermodynamics, which is some deep statement of statistical mechanics in general, if we believe various guesses, translates into a geometrical statement which you can prove as a theorem in Einstein's general relativity. And this has this has deep and profound consequences, some of which we understand, some of which we don't. Okay? The fact that areas of event horizons always increase and never decrease, there's a second theorem of general relativity that I'm just going to allude to now, and we'll try to understand in more detail later. The second theorem which says that the event horizon of a future that future event horizons can never bifurcate. Bifurcate, which means suppose I have the following process is allowed. You can have a future event horizon whose space-like slice is two spheres, and it becomes one. But the reverse is never possible. You can never have one sphere becoming two. Okay, now these two statements together tell you something very important. You see, this event horizon roughly is the event horizon of a black hole, more or less what a black hole is, Schwarzschild solution. What does it mean that the event horizon, its area always increases? Roughly speaking, it means you cannot extract energy out of a black hole. This is a bit inaccurate because when black holes have charge or when they're rotating, you can, but you can never do it in a way that decreases the area.
How does it mean that?
How does it mean that? Very good. It means that because when you compute the area of the event horizon, let's do this as an exercise. I mean, it's okay. It's too trivial to be an exercise. Let's just work it out on the board. We had this on the board. Suppose I take a particular slice. Okay. So let's look at this metric on the board. Let me do it in Gaussian coordinates. dS squared is equal to 1 minus beta by r d v squared plus 2 dv dr plus r squared d omega t squared. Okay, now suppose I look at the surface r is equal to beta and v is equal to fixed. This is now a two-dimensional manifold because I've specified two coordinates. Okay, what is the area of this two-dimensional manifold? 4 pi r squared beta squared. That's 4 pi beta squared. You understand? Because these two terms don't contribute. So on this two-dimensional manifold, the metric is just this, but with r replaced by beta. But you remember that though we hide the fact beta is 2m. So the area of the event horizon was 4 pi times 2m the whole thing square. Okay, so whatever it is, 16 pi m square. Now, if we stick to black holes that are not rotating, these kind of Schwarzschild black holes, area not increasing means m increases. Okay? Now, I said it a bit inaccurately because the theorem is that the area cannot increase. There's no theorem saying the mass cannot decrease. There's no theorem saying the mass cannot decrease. And in black holes that have some rotation or some charge, sometimes you can decrease mass while increasing area. So those processes are allowed. But roughly speaking, I mean, if you think that the area is a measure of the size of a black hole, it means no matter what you do to a black hole, it cannot get smaller. Okay. Now there's also the statement that the black hole, the event horizons of black holes cannot bifurcate. So it means that you cannot take one big guy and break it up into two smaller guys such that the area increases. But each guy is smaller, you can't do that. What does this mean? We'll end just for fun. What it means, if you think about it, is you cannot destroy a black hole. What does destroying mean? You had a big rock. Say you had a big asteroid coming towards the Earth. Hey, you want to demolish it. What can you do? Well, either you could pulverize it, meaning do a nuclear experiment to turn it into photons. Or more likely, what you could do is break it up into many small little bits, such that each bit is not too lethal. Each bit can be knocked off its course. For black hole, you can't do either. You cannot make it smaller than it was, and you cannot break it into two parts. So if you had a black hole coming to the
violent process is,
what?
however violent that process is.
However violent, this is a theorem of classical general relativity. The only way you can do it is by violating one of the assumptions in the theorem. So go to quantum mechanics or some of the reasonable assumptions that go into quantum. So if you had a black hole coming towards the Earth and you sent the US nuclear fleet at it, no good. It won't blow it up.
It would help them. It would grow larger.
All the size you said is like the size of the event horizon, right?
Yes. Everything I'm saying is the size of the event horizon. And you have to ask, and it's a good question, is that a fair way of assigning size to the black? Because what does size even mean in general relativity?
Because you could fall beyond it, so it's not really the size.
But what does it mean? It means the event horizon is a measure of the space beyond which space is approximately flat. Right? So see, suppose we have a rock. What do we mean by the size of the rock? What we mean is, how much space do we have to exclude so that outside that we're in empty space? So in the same way, if we've got a black hole, roughly speaking, for any precise question you need to give a precise answer. But roughly speaking, what you mean is how much of the space-time manifold you have to exclude so that outside it, the space-time is roughly Minkowski space. Clearly the measure of that is r is equal to beta. I go to 10 beta. This is almost like Minkowski space. So in any reasonable way of thinking of the size, that is the size of the event horizon. Okay? So it's a very deep theorem about, and it's related to the second law of thermodynamics. Okay, there's many interesting things to say about this that go beyond words. There's the equations that underlie everything I'm saying. And I'd love to discuss this. It's great fun. But we'll first do the bread and butter stuff. So next lecture we'll do either cosmology or gravitational waves depending on what we feel like, and the other one next. Any questions or comments? Otherwise,
I have taken only the normal to generate the components of this. We can take any other vectors?
you could take any other vector, but what you need is a vector field. No, it's a more serious question. You see, the thing is this.
Is that the only geodesic components are there?
It's the only set of null geodesics on the only set of null geodesics on the surface. Let me try to explain why. Let us first understand that there are no time-like geodesics on the surface. Physically, it's actually, in this diagram, it's totally clear. Right? Okay, but physically, this is the point. You see, what is a null manifold? A null manifold is a manifold in which, if you write on a basis of vectors, you can choose a basis in which there is exactly one null vector, and all the rest are space-like. Okay. So there's basically a distinguished direction that is not space-like. Any other direction, let me say it this way, let's say it physically. Any other direction you try to shine your light ray, it will go into the singularity. There is one direction which is the best possible way, which in this case is flat radially outwards, which will just stay at the event horizon. Anything else, you're losing steam. You're wasting some of your velocity vector, going some other direction. You'll just hit the singularity.
And if this have any other vector to calculate?
Yes, at any given point, there is only one direction in which you can move, in which you are going to be null. That is what this equation is. So you define a unique set of null geodesics that generate the manifold, that lie on the manifold, on the submanifold. Okay, we'll come back to these things hopefully soon.